and Gavin, you can take notes, but every once in a while check to see if that's on. Okay. 14.1 is understanding rational exponents and radicals. Okay. And objectives are, so how are radicals and rational exponents related? And how do we compute radical and exponential expressions? Or simplify. Let's say simplify. Recall that an exponent represents repeated multiplication. What does that mean? What do I mean when I say an exponent represents repeated multiplication?
Like it multiplies itself?
Repeatedly.
Oh, repeatedly, yeah.
Right? So, and this is one of the ways that math is nice, fits nicely together. Okay? We have addition, and multiplication is repeated addition. Then for multiplication, if we repeat multiplication, we get exponents. So addition, repeated, yields multiplication. So I can add 4 and 4. If I add 4 to itself 10 times, that's called 4 times 10. So repeated addition is multiplication. There's a similar relationship. So the relationship between addition and multiplication, there's a similar relationship between multiplication and exponents. Okay? So I can go 2 times 2. But if I go 2 times 2 times 2 times 2 times 2, that's 2 times itself 5 times, that's 2 to the 5th. Okay? So repeated multiplication, an exponent represents repeated multiplication. And that's old news. Okay? Also recall that a root represents, quote unquote, undoing an exponent. So, I mean, you could also say that it represents repeated division, right? But essentially, so a square root is saying, well, the square root of 9 is 3 because 3 squared is 9, right? So we undo, so if I take the square root of 9, I'm undoing the squaring of the 3. Okay? So just kind of remember that relationship between exponents and roots. Now, have you dealt with square roots? Yes?
Yes.
Okay. Have you dealt with cube roots?
Right, maybe. I don't know.
I don't believe so.
Okay. So today, we're going to deal with roots that are more than square roots. Okay? And I'll show you the way for writing them. But we're talking about such as like, who could tell me what's 3 cubed?
9. No, what am I saying? 27.
27. 3 times 3 times 3 is 27. So 3 cubed is 27. So the cube root of 27 is 3. Okay? So roots. Okay? So when I say roots now, I'm not in this particular module. I'm not just talking about square roots. I'm also talking about cube roots, 4th roots, 5th roots, 6th roots as appropriate. Okay? And we're not going to have to, you don't necessarily have to know them, but you have to know how to identify where they are in an expression. Okay? So let's see. First, I want to show you 3 basic cases of integer exponents. Okay? So consider these 3 cases, and remember, when I'm writing things on the board, you should be writing them. Okay? 3 kind of broad cases. There's when we take a number x to the integer n. This is our typical case of an exponent that we're familiar with, where it means x times itself n times. Okay? And we could even say multiplied by itself, okay, which would make that sentence less redundant. X multiplied by itself n times, right? Old news, yes? And I'm presenting this information a little bit differently than the book, because I'm presenting it kind of in more systematic chunks. So if you look at the lesson in the book, it will present it a little differently. I think this is cleaner, okay? X to the 0 always equals 1. Okay? So negative 72 to the 0, what is that? Negative 72 to the 0 power. 1. 5,370,201 to the 0 power. What's that?
1.
1. Anything raised to the 0 power is 1. Okay? Anything raised to the 0 power is 1. Because think about it. You're multiplying something by itself no times. Right? So there's nothing there. So since we're dealing with multiplication, 1 is nothing. Okay? It's the identity. So 1 is the multiplicative identity. So multiplying something by itself no times returns the identity. Now, if I have x to the negative n, so notice in this case I'm saying specifically here that n is positive in this first case. Now I'm saying explicitly here in the third case that n is negative. It's a negative integer. Okay? A negative integer or rational number. A negative rational number. Then we get this equals 1 over x to the n. So if I have a negative exponent, that expression goes in the denominator. Or more precisely, which also means it goes to the opposite side of a fraction. So if I have a negative exponent that's already in the denominator, I can move it to the top. Okay? And the exponent becomes negative. Or positive, sorry. A negative exponent in the bottom gets moved to the top, and that exponent becomes positive. If there's a negative exponent in the top, I move that expression to the bottom, and the exponent becomes positive. Okay? You follow me? So for instance, 3 squared is
9.
9. So that's our first case, right? A positive exponent just means 3 times itself 2 times. 3 times 3, 9. 3 to the 0, anything to the 0 is 1. Okay? And 3 to the negative 2 equals 1 over 3 to the 2 equals 1 over 9. So this is how we deal with positive, negative, and 0 exponents. Okay? So that's your first batch of information. Tell me when you've got that.
Got it.
Cool.
Oh, got it.
Okay?
Got it.
Okay. Alright, now there are 2 rules for what we do with exponents in an expression. How they start working together. So I'm going to erase this, okay? Are we still live?
I think so.
Is the little green bar on the bottom rolling along?
Yes, it is.
Fantastic. Okay. So, I just wrote, on my notes I wrote also dot dot dot, okay? A new section, new little break. X to the n, all raised to the m power, okay? This is how you say it. Power to a power you multiply. Say that with me. Power to a power you multiply. One more time. Power to a power you multiply, okay? Power to a power, n to the m, x to the n, all to the m, so power to a power, you multiply. This equals x to the n times m. Okay? So if I'm raising a power to a power, I multiply the exponents. Okay? I'll show you an example in a moment. Also, if I have two terms with the same base, well, they're not terms because they're not being added, two monomials with the same base. This right here is called the base. This is the exponent. Okay? Two monomials with the same base and different, or exponents don't have to be the same, but in this case, they don't have to be different, but they can be the same. If I'm multiplying two monomials with the same base, I add their exponents. So this equals x to the n plus m. Is that old news?
Yeah.
Yeah.
Okay, cool. So then that's a recall. Alright? But I just feel like it's good to deal with this when we deal with this. But this is not old news, right? Or is it? Old news or new news?
I think I've seen
No, I
that
think-
before.
Okay. Well, cool. There you go. They did deal with it in the book. They kind of like mention it in passing, like, you know, power of a power property. So I didn't know if you'd had it before. So those are two things we need to know. Then further, we have fractional exponents. Okay? So we've dealt with like positive integer exponents, negative integer exponents, and zero, and the exponent with it being 0. Now I want to talk about what happens when the exponent is a fraction. Okay? Yep. So x to the 1 on n. Okay? So that the base here is x, the exponent is 1 on n. Okay? That means the nth root of x. So for instance, if we said 9 to the 1/2, okay, that equals the square root of 9, which equals 3. Now, when we see a this is called a radical symbol. This is called a radicand. Okay? What's inside the square root house is called the radicand. The square root house is actually called the radical. Okay? When you see, and then the number that goes here is called the index. When you see no number here, it's an implied 2. So I'm going to write a dotted 2. Okay? You can't tell from there that it's dotted, but it is. Right? So there's an implied 2. Just like when there's no exponent, there's an implied 1. Or when there's no coefficient on a variable, there's an implied 1. Right? Here, when there's no index, there's an implied 2. Alright? But let's say, for instance, that I was dealing with another example. Right? Let's say 8 to the 1/3. Okay? That equals the cube root of 8. Now, my radical has an index. So I'm not saying what times itself twice equals 8. I'm saying what times itself 3 times equals 8. This is a cube root, not a square root, a cube root. So that where we get those words is like a square root is saying like, if I had a square whose area was 9, what's the side length? Okay, so I take the square root of 9 is 3. In this case, I'm saying, if I have a cube whose volume is 8, what's the side length, an edge length? Okay, so in that case, is what times itself 3 times equals this. So in this case, that is 2. The cube root of 8 is 2. Okay. So cube written this way and this way are the same thing. 8 to the 1/3 and a radical with an index of 3 over with a radicand of 8. Same thing. Okay? So notice we're going to be able to use this if we're trying to, let's say that there's a variable in here and we're trying to multiply an expression out. We have that variable somewhere else with some integer exponent, and then we have that variable inside of a radical. I can transition this radical to a fractional exponent to be able to make it play nice with the rest of the expression. You understand what I'm saying? We'll work on some examples in a moment. Okay? So furthermore, building on that, okay, if I have x to the m over n, okay, well, m over n is just 1 on n times m, right? 1 on n times m. So 3 halves is just 3 times a half, right? Everybody with me? So in this case, I have x to the 1 on n, well, x to the 1 on n, 1 on n times m, that's all in my exponents, okay, equals x to the 1 on n to the m. Which equals the nth root of x to the m. Okay? So these expressions interchangeable. So we can move back and forth depending on what we need, depending on what kind of expression we're working with. Okay? So for instance, let's say that we had 8, yeah, let's say, so for instance, i.e. 8 to the 5/3, right? So my exponent here is 5/3. Well, I could write it this way, right? Equals the cube root of 8 to the 5th. Which equals 2 to the 5th, which equals 32. Nope. Equals, no, that's right, 32. That's right. I had it memorized and I doubted myself. Cool? That's all the content. Shall we do some examples? Yes or no? No examples?
Sure.
Okay. Fantastic. Alright. So, for instance, okay. No, 25, yeah, 27 to the 2/3. Okay? 27 to the 2/3. So that means I have a 3 in the denominator, so it's the cube root of 27 and I have a 2 in the numerator, so it's squared. And just a reminder, this equals 27 to the 1/3 squared. Okay? Those are equal. So what's the cube root of 27? We talked about it earlier. Somebody other than Gavin? What times itself 3 times equals 27? 3. So now I have 3 squared equals 9.
Well, this isn't too hard.
No. So that all we're doing is simplifying an expression. 27 to the 2/3 equals the cube root of 27 squared. Cube root of 27 is 3, squared is 9. Okay? How about 25 to the 3/2? Are we still rolling along?
Yeah.
Okay. 25 to the 3/2. So what's my root and what's my exponent? Like what am I, you know what I'm saying? When I have a m over n here,
Your root's going to be 25.
yeah, the radicand is 25.
Okay, so then the root would be 3.
Yeah, the index on my,
Okay, so
Radical.
the index is going to be 3.
nope,
2.
2.
Oh.
So there's an implied 2, but I'm going to write it in just so we know what we're talking about. And then the remaining exponent is a 3. Okay? Because again, I can rewrite this as 25 to the 1/2 all cubed. Okay? And 25 to the 1/2 means the square root of 25. So that equals 5 cubed equals 125. Just as a note, exponents only operate on what they touch. So, like, this 3 is operating on these parentheses, so it operates on this whole thing. That's going to come into play later, okay? When we have some more involved expressions, okay? Yeah, we don't deal with exponents on variables in this lesson, okay? Cool? So hit stop on that stream.